I have a video on YouTube that describes how to use the ODE 45 routine in MATLAB to solve ordinary differential equations numerically. And this phrase here on this slide was one of the comments of that slide. One word, Simulink. And the inference here is that we could use Simulink to do that problem and apparently much easier. So what I'm going to do here is show you how to solve a differential equation numerically using Simulink. So that's what this is about, using Simulink to solve ordinary differential equations. Um, there are many built-in solvers to solve ODEs in MATLAB in the basic part of MATLAB, and almost all are based on the Runge-Kutta routines, and they're of different order, and some for solving stiff equations and things like that. Simulink is a different tool. It's much more graphical or visual, and it's really designed to solve complex systems. So you take systems which are made of a bunch of components, you build a model for that system by dragging components onto essentially a worksheet and connecting them with lines and then adding parameters to those systems and solving it. So if you want to learn more about Simulink for those kinds of applications, you can Google Simulink and you'll find lots of information out on the internet for that. What I'm going to do is specifically use it to solve an ordinary differential equation. Here's what a typical Simulink model looks like. There's all these little boxes and triangles and things. Each of those has a particular, carries out a particular operation. There's an input to a box, and then the box acts on that signal, and then delivers an output signal. And by connecting all these boxes together, you can do a variety of things. This is just a typical model that I downloaded from a website at the University of Michigan. Okay, again, I'm not going to go into great detail in Simulink. So to show you how to solve a differential equation, this is our model system. It's a typical linear oscillator. It's damped and forced, right? So X is the displacement of that oscillator. Think of a mass connected to a spring with some kind of damper associated with it. This is the damping term, 3dx dt. This tells you the strength of the spring, essentially the 4x term, and then the forcing term is here on the right, 5 cosine of 2t. Since it's a forced oscillator, I'll just start with initial conditions, which are 0. So we start with the oscillator at rest and no initial velocity, right? So the initial position is 0 and no initial velocity. We turn it on, the forcing will induce the motion, and we want to calculate the position of this oscillator as a function of time. Okay, in order to prepare that, what I usually do, at least for Simulink, is solve for the second order term in terms of everything else. So the second derivative of x is the forcing term minus the damping term minus the spring term 4x. And this is what the Simulink model looks like. So this stuff up here on the upper left is the forcing term. The output end result of this is the 5 cosine 2t. And then all this other stuff is the rest of the differential equation, and this little scope is just for output. So what I'm going to do is zoom into to the separate portions, the input and the output, and show you how those work. So here's the input. Again, the input is this term here, 5 cosine of 2t. So the clock here produces a time signal. This triangle here is a multiplier, and the multiplier is 2, so it takes in a signal for t and outputs 2t. This is a trig term, cosine, so it takes 2t and calculates the cosine of 2t. So this output here is cosine 2t. Then we multiply by 5, we get 5 cosine of 2t, and that's this forcing term. All right, so just by dragging these blocks around, and I'll show you how that works in a minute, we get this forcing term. Now let's look at the rest of this. So again, that input signal is coming here. Okay, and the rest of this is for modeling the equation. So we think of the output of this circle here, which is just adding and subtracting some signals. Okay, the output here is the second derivative of x. So if this is d squared x dt squared, this box here is an integrator. The 1 over s term is an old thing from looking at things in the frequency domain. If you don't know where that comes from, don't worry about it. It's just that this box takes this and integrates it. So the integral of d squared x dt squared is dx dt. So the input is the second derivative, the output is the first derivative. We integrate that once more, and the output is x. So we have a signal for x dot, a signal for x, and a signal for the second derivative. So we need, this is our differential equation up here. So we need a term for the damping, which is 3 dx dt. So I take this dx dt term, run it through a multiplier, and the output is 3 dx dt. And we need a term 4x. So we take our x, we run that through a multiplier, and output is 4x. So this is this damping term, this is this spring term. So if I take my input signal, which is 5 sine of 2t, subtract off the 4x, subtract off the 3 dx dt, then that should all equal the second derivative, right? So based on our equation, this little thing puts together the equation, and if the system runs consistently, then that should be a model for our differential equation, all right? This helps us look at the output. So basically, this coupled with that other picture on the left, which puts together the forcing term, is our model for the differential equation. And if you want to change some of these parameters here, the 3, the 4, the 5, then you can just right-click on these operators, and it'll let you change the constant inside there from a 4 to whatever you want it to be, or from a 3 to whatever you want it to be. Right? We do need to set some initial conditions. Those are set, again, right in the integrator blocks. So if you go into those integrators, the two squares with a 1 over s inside them, then you can right-click those and set the integrator parameters, and that will let you set the initial value. Okay. So now we've got the equation modeled and the differential and the initial conditions modeled, and we just need to run the system. So what I'm going to do is switch you over and show you how Simulink works, how you kind of drag these boxes around to create these models, and then how you run it and how you look at the output.